Okay, so now we talked about how to calculate moment of inertia when we had just a series of particles. Well, now we're going to talk about it for a rigid or solid body. This is a little more challenging because we have to use integrals. Okay, fortunately, well, let's go ahead and show it this way and then we can talk about some shortcuts. Okay, so basically, we take each point, or each, rather, disk, multiply it by its r squared and its dm, so however much tiny little bit of mass it has. Okay, and we add all those up and we get our moment of inertia. Okay, well, let's pretend that this is a cylinder. Okay, and we're going to be rotating it around its kind of central axis going through the middle of it. Okay, and so it's going to be rotating like this. So basically, we can kind of look at this face as a disc. So if you could think of, like, if you were to take a quarter and lay it flat on a table and spin it like that, it'd be something like that. Okay, and so we want to find its moment of inertia. Well, what we can do is we can slice it up into these infinitely tiny radii. Okay, and so we're going to say the density of this shape, we're going to kind of walk you through how we get there. So the density is equal to the mass over the volume, and for each little slice, it's going to have density of dm over dv. Okay, well, the volume, well, let's do this. Okay, so the volume of a cylinder is going to be the area of its face, 2 pi r squared times its length. Okay, and that's over m, and that gives us density. Well, the ratio of the change of the rate of change of mass with respect to volume is going to be the same. So if we take the derivative of this with respect to r, we get 2 pi rl dr. Okay, and so we're going to say, if we want to replace the dm here so that we can integrate with respect to r, and so we're going to say that rho equals dm over 2 pi rl dr. And we're going to go ahead and solve that. So dm equals rho times 2 pi rl times dr. So we can take all this and substitute it right there. So we get that I equals the integral of r squared times 2 pi r l dr, and then we can't forget to add rho in there too. So let's pull all the constants out. Rho is a constant, pi, l, and 2 are constants. So we get 2 pi l times rho times the integral of r cubed dr, and we're going to integrate this from 0 to r, which is the radius of this shape. Okay, so we integrate this and we get 1/4 r to the 4th. Okay, we're going to evaluate from 0 to r. Okay, which just gives us 1/4 r to the 4th times 2 pi l, the length, times rho. Okay, and that's our moment of inertia. Well, that's pretty messy. Fortunately, we have this, what we defined right here. Okay, that rho, the density, is the mass divided by the volume, and we can stick that in there for rho. Okay, so we get 2 pi l times m over 2 pi r squared l times what we just got here, 1/4 r to the 4th. Okay, so the 2 pi and l will all divide out. 2 of the r's will divide out. Sorry, I apologize. I made a mistake here. We get the 2 when we take the derivative. There's no 2 right here. So that 2 doesn't cancel, but it can cancel with this one. Okay, so there was no 2 in there, that was missing. So anyway, we simplify this mess and we get that I is equal to 1/2. 2 of the r's cancel out too. So m times r squared. And so the moment of inertia of this disk, as well as all other disks, is equal to 1/2 mr squared. So here's another shape. It looks exactly like the one we just did, but let's pretend that instead of this being a disk, let's say it's like a hula hoop, so it's just like a ring, which means that all the mass is located on the outside. So for this one, it's actually really simple. The moment of inertia for this guy is just m times r squared. Okay, because all that mass is on the outside. We don't have to add up any other dm's. All the m is located here. Okay. So we're going to do one more. Let's say that this is a meter stick. Okay, it's 1 meter long, and I want to twirl it about its center, cause it to spin this way. Okay, so I want to measure the moment of inertia for this rod. Okay, well, we're going to do the same process. Alright, but this one is going to be a little bit easier for us. Okay, because we're going to define dm by saying that m over L is the same for every point in this rod, which means that dm over dl, instead of dl we'll say dr, which we're using r up there, is going to be the same at every point as well. So that means that dm equals, you might recognize this when we did center of mass, m over L dr. Okay, you can take this and put it right there for dm, so we get I equals the integral of r squared times m over L dr. Okay, we can pull this m over L out to the front. If we're rotating about the center, this would be like radius of 0. This would be maybe L over 2. We could say this was like negative L over 2. And so we want to integrate from negative L over 2 to L over 2, okay, for the 2 radii. Alright, so what we can do now, we have m over L. If we integrate r squared dr, that's going to give us 1/3 r cubed. As we said, integrate from negative L over 2 to L over 2. When we plug those in, we get 1/3 L over 2 cubed minus 1/3 times negative L over 2 cubed. Okay? And so when we simplify, L over 2 cubed is going to be L cubed over, I believe, 8. So that's going to be L cubed over 24 minus, over here it's going to be negative L cubed over 24. Okay? You subtract the negative, you add them, so we get m over L times 2 over 24 L cubed. Okay, to further simplify, we can cancel out L from here and there, and 2 over 24 simplifies to 1/12, so that we get 1/12 ml squared for the moment of inertia for this uniform rod. Okay? Okay, so what you may have noticed by now, and what's going to make our lives a little bit simpler, is that because it's so much work to find moment of inertia through integrals, the book and the AP test, they kind of give us a shortcut by telling us the moment of inertia for the most common shapes. And if you look on here, this is actually straight out of your textbook. You'll see 3 that we looked at. So for a hoop, it's mr squared. For a solid cylinder, it's 1/2 mr squared, okay, which we proved for the first one. And then for the last one here, a thin rod about an axis through its center that's perpendicular to the length would be 1/12 ml squared. And these are probably the 3 we'll use the most. Occasionally we'll use some of these other ones. A sphere will be important later. Okay. But you would want to memorize probably these 3 and maybe this one. Okay? So these are the moments of inertia.